let's proceed. Now, last elementary property of this integration is about estimates. So let's discuss length of a curve. So suppose we have gamma, complex numbers, and it's differentiable. So then the length, so this is definition, the length of gamma is defined as, so how would you imagine it? You are going by car on a curvy road, so how do you measure the length of the road? You integrate the absolute value of your speed, right? So, so then this is defined as so now using the length, we have the estimate for integration. Yeah. So remark if gamma is piecewise differentiable, and then length of gamma is defined as sum of length of differentiable pieces. So the proposition about the estimate. So suppose that we have a function which is, so we have a curve first of all, and a function f on the image of this curve to C continuous. Then the estimate on the absolute value of the integral is the following. So let's say that the function is less or equal than some constant by absolute value, then the integral is less or equal than m times the length of gamma. Well, it's basically applying one of the previous lemmas, which we proved. So the proof is simple. The absolute value of integral of f of z dz over the quasi gamma is absolute value of integral from a to b f of gamma of t gamma prime of t dt. And then you remember we spent one board to prove that this is less or equal than integral from a to b of absolute value of f, absolute value of gamma prime of t dt. So then this is less or equal than m, which is estimate on f, on absolute value of f. And what remains is exactly our definition. Sometimes I put dash, sometimes I put dot, but this is okay, so this was easy. Now let's talk about the central topic of today's lecture, which is primitives for functions. So I'm not specifying this more explicitly for the reasons that we need. So there's a difference from what we had in one-dimensional, so real analysis. So it will be important to specify domains of definitions. For f of a special kind. So certainly a disk would be good, a square would be good, but if you draw some random, very complicated curve and take what's inside, this could be less good. So definition, we call an open set G in complex numbers a domain. So I'd like to say if it is path connected, but technically proofs require more, even though I think it's an equivalent property, but I'll state what I really require. If for any 2 points, Z0 and Z1 in G, so I mean, it's open already, but also for any 2 points, there exists what I'll call ladder path from Z0 to Z1. So let me draw what I mean and you'll understand better than any formulas. So we have 2 points, Z0 and Z1, and a ladder path is a path, so I mean, this is a complex plane, so in particular it's R2 with chosen coordinates, the real line and the imaginary line. So the path should be divided into finitely many pieces which follow either horizontally or vertically. Okay. In this sense, it's kind of a ladder. No. So there should be finitely many of them, and either horizontal or vertical. So you can imagine that any disk, or more generally any convex shape inside complex plane will be like this. But I mean, it could be that you can draw something really bad, which is not like that. Good. So this will be our domain of definition. So from now on, functions we consider will be defined in domains. So now we come to the central definition. The definition. So for G, a domain. F from G to complex numbers is primitive of F, sorry, G to complex numbers, if, well, first of all, F is holomorphic, in G, and second, is derivative equals small f. So finding a primitive is the operation opposite to differentiation. Yeah. So an obvious remark is let f1 and f2 be primitives for f, g, and numbers. So both of them are primitive. But then, of course, f1 minus f2 prime is f1 prime minus f2 prime is f minus f is 0. So we have a holomorphic function with derivative equal to 0. So it's a constant. There exists a constant k. F2 is F1 plus k. So if one primitive exists, then any other primitive differs from it by a constant. Now, existence of primitive is a question, and it's so that's what we'll deal with. So examples of primitives. Well, for f being a monomial, and G can be chosen to be the whole complex plane, a primitive could be chosen to be z k plus 1 over k plus 1. For f of z being exponential function of z, of course, f of z can be chosen to be exponential function of z. And again, this is for G being the whole complex plane. Yeah, so we can talk about sine and cosine. I won't do it right now. But more generally, so using what we studied last week, we can treat a more general example. So suppose that f of z is given by sum of series a n z minus z naught to the n, not necessarily around 0, say around some other point z naught. So for z in some disk around z naught of rho, so converges absolutely. And then, as we know, the series f of z, which is defined as some, so first of all, some constant k plus some n greater or equal to 0, a n by n plus 1, z minus z naught to n plus 1. 0. Also so has the same radius of convergence. Is holomorphic. And k z naught rho, and its derivative equals to f. So this is a typical example of a primitive given by series and defined in a disk. So our domain in this case is this disk G. Great. Now there's an easy statement. So maybe since it's easy, I'll here. Lemma. I don't think it deserves the name of a theorem. It's easy. So a function, so G is a domain. F defined there has a primitive. And then suppose we have a path gamma a, b to g, so lands inside this domain. So we should think about some domain and a path in it. Yeah, then the integral from a to b f of z dz, sorry, along gamma f of z dz is simply, yeah, so let's call these points, so gamma of a is z1, gamma of b is z2. So then this is the difference of values of the primitive. So if you think about it, that's exactly like the formula we had on a line. So on a line, if we have a primitive for a function, then integration is just taking difference of values of primitive. Only here we have more freedom. We don't have only points, we have also a path between them. But now the statement is that, right, left-hand side depends on the path, right? So we are integrating on some curve on this g. But right-hand side doesn't depend on the path. It's just difference of values of some function. Right? So maybe I should put this as a remark. A priori, left-hand side depends on gamma, but right-hand side depends also only on endpoints, on z1 and z2. So in a way, this was less surprising when we talked about intervals on a line, because an interval is a pair of points, the beginning and the end. But here we have lots of freedom, but it turns out that all paths from this point to this point have the same integral. Good. So let me prove it. So the proof is surprisingly easy. It's just a calculation. So the integral over gamma f of z dz is, so let's just substitute. It's integral from a to b f of gamma of t, gamma prime of t, dt. But f is capital F prime. So this is the integral from a to b, f prime of gamma of t, gamma prime of t, dt. But now we see that this together is a full derivative of a function. So this is integral of a to b, f composes gamma prime of t dt. So now we are in this situation that we have f composes gamma. It's a differentiable function from a, b to complex numbers. And yeah, I mean we can use one of the rules of integration. So by one of the rules of integral, this expression is simply f gamma of b minus f gamma of a. But this is simply f of z2 minus f of z1. So in a way, we have maybe not extremely easily checked, but very strong condition on functions to have a primitive. And this condition is independence of integration on the path. So maybe to emphasize, that's where it becomes important how we define the domain G. The domain G in particular restricts paths we consider. So let me try to see the remark. So a choice of G is important for existence of a primitive for F. So indeed, let's take a look. We have this area called, or domain called G1, and a bigger one, call it G2. And suppose we have 2 points here, Z1 and Z2. Then we have a function f which is defined even on the bigger one, G2 to C. And we ask whether f has a primitive in the smaller one and in the bigger one. So this previous lemma gives a criterion. So any path in G1 is like this, but we can consider paths which don't stay in G1 and go also to G2 and then return to G1. So the condition that f has a primitive inside G1 means that the integral along every such path is the same. And it's just difference of the value. But we can also ask about paths which go outside into the bigger one. And maybe if we go outside, the integral will be different. And so in this lemma, it's important which domain we choose, and this just restricts the class of paths we consider. So good. So could satisfy the lemma in G1, but not in G2. Okay, now let's prove the one of the central statements for today's lecture. Lemma. So G is a domain. The function f from G to complex numbers, and it's continuous in G. So suppose that f has integral equal to 0 along any closed staircase path. In G. So we have this G, and then we have this closed staircase path. I'm not the best artist you can imagine, but this is gone. Then f has a primitive. In the domain G. So let's see. The other direction would be clear, right? So we have if we have a closed path, then we can choose its beginning and the end, and then there'll be 2 paths this one, and just a constant one. And the previous lemma says that the integral should be the same. Right? So then I mean the difference. Okay, I'll write it carefully. Remark. So the converse is clear. If f prime equals to f, then by the previous lemma, take two paths, so z1 equals z2, and one path is just constant, so gamma 1 is constant at this point. So it never leaves the point. And gamma 2 is our staircase path, closed staircase path. Path from gamma to gamma, or from z1 to z1. Then, by the lemma, the integral of f along gamma 1, and gamma 1 is just constant path, so it's just 1 point. So then, integral over 1 point, of course, is 0. Equals integral over gamma 2 of f. And this is random staircase path in our domain. So if the primitive exists, then any such integral is 0. Now we're proving the interesting direction. If such expression is 0. So we'll see where the tricky part is. So, so first of all, suppose the condition is satisfied for any staircase closed path gamma. So fix 1 point, fix z node. Put capital F of z equal integral over gamma z of f, where gamma z is any staircase path from z node to z. So let's discuss it. First of all, why does such path exist? It's one of the conditions in the formulation of the lemma. So G is a domain. It means that any 2 points are connected by a staircase path. Second, why is this expression independent on a choice of this path? It's because we have this z node and this z. This is one staircase path, sorry. And this is another one. Why are these integrals the same? For the obvious reason that if we go along one of them and return by the other, on one hand we are integrating along this closed staircase path. On the other hand, using the condition 0. So integral over gamma z prime f plus integral over minus gamma double prime z f is 0. But then it means that integral over gamma prime z f equals minus integral over minus gamma double prime z f, which equals integral over gamma double prime z f. So if this one is gamma prime z, and this is gamma double prime z. So if we go along one and return by the other, so the sign means that we're returning, but it results in the minus sign, which cancels with the other one. Good. So it's a well-defined function. So what remains to prove is, now let's discuss what remains to prove. It seems that we found a function. What remains to prove actually is that it's differentiable with derivative f. So we need f defined like this. Is homomorphic with f prime equal to f. Okay, let's prove it. So let's draw a picture. So this is our domain G. Somehow this is Z node. This is Z1, at which I'll choose. I'll check differentiability. And of course I'll choose a little disk here of some radius. So it will be K of Z1 with some radius R. So I'll choose a staircase path from this to this, and then further, so there'll be Z1 plus H, because I'll do limit formula for derivative. So let's write our estimates. Capital F of Z1 plus H minus capital F of Z1. What is it? It's I will just show on the picture and then write the answer. So capital F is integration along any staircase path. For example, via this one, I drew it. So one value is going from here to here, so we go all the way. The other value is going from here to here, so going only part of the way. So the difference will be going along this path. Call it L. So it's a path from Z1 to Z1 plus H. So this is integral over L f of Z dz. Okay. So also notice that if we take any constant, the integration over L of this constant will give us just well, so it's the value of the function z at here minus at here, so this will be c times h. So for any constant c. Then let's write 1 over h f of z naught plus h minus f of z1 plus h minus f of z1 minus small f of z1. So this will be our constant. So then this will be 1 over h integral over this path L. So this difference we wrote as integral of f of z, and this becomes integration of constant. Very good. So now, well, we'll do absolute values. So choose this R small enough so that f of z minus f of z1 by absolute value would be less than epsilon. Then we are estimating absolute value of 1 over h f of z1 plus h minus f of z1 minus f of z1. So we expressed it as an integral, so this is equal to 1 over absolute value of h, absolute value of integral over L f of z minus f of z1 dz. And we know by one of the previous lemmas that this is less or equal than the length of this path L divided by absolute value of h, and then the maximum of value of absolute value of this difference, which is epsilon. And now we're using that we did staircase path. So, and no matter which. So we have 2 points, and so h is this. So it's this is z1 plus h. So h is this. So it's, absolute value of h is this piece. Now, what's the length of the path? It's a staircase path, and it can be chosen in any way without cancellations. But the point is that if we sum up all these, we'll get just the sum of sides of the triangle. So this is h1, this is h2, and this is absolute value of h. So this is this equals h1 plus h2 h, and then times epsilon. And then you can ask yourself what's the maximal ratio of the sum of catheta and hypotenuse. So it's the in the triangle. Well, and you can estimate by 2. I think you can estimate even better, but you can estimate it by 2. So we used explicitly that this was not some random path from this point to this point, but a staircase path. Good. I proved differentiability, so I proved the lemma, and it turns out that this is basically the main technical statement in the whole section. So let me finish today's lecture with a theorem which has surprisingly easy proof, and I hope that in these 5 minutes I'll both formulate and prove it in view of what we've done already. So theorem, we have a function from a domain G to complex numbers. The following statements are equivalent. First of all, f has a primitive. Second, the integral over gamma of f, so now gamma is not a staircase path, but just any path, is, so depends only on gamma of A and gamma of B, not on gamma itself. And finally, so gamma any path. So for any closed path, gamma in G, again, it's not staircase path, it's just a path. The integral of gamma of f is 0. So now the proof is almost trivial because we did almost everything for it. So proof 1 implies 2. So this is one of our previous lemmas, that the value of the integral for a function having primitive is the difference of values at the end. So clear. 2, 2, 3. Also clear because, well, any closed path can be considered, so this is my z1 equals z2. It's the consideration I discussed on that blackboard. So the integral over this closed path, gamma of f, and let me denote by gamma 0 the path which doesn't go anywhere, is gamma 0 f, so it stays at this point, and it is 0. This clear because now the only part to prove is 3 to 1, and and we actually proved it. So if 3 holds for any path, it holds for any staircase path, or closed staircase path. Then use the lemma. And it's, so the lemma says that if integral over any staircase path is 0, then there's a primitive. So, good. So it was a relatively